Hello and welcome to the video solutions here for this Core Pure mock exam paper. Now you're more than welcome to use this paper here as a predicted paper for the upcoming 2025 exam series. Now, it isn't actually designed as a predicted paper. As you can see on the screen here, it just says mock exam paper. And that's what we designed this as, right? So if you go over to our website, AJMaths.co.uk, we've also got these for A-level maths. We've also got A-level maths mock exam papers. And these here are just designed to be kind of like replacement papers for A-level maths and A-level further maths. But of course, you can just use these as predicted papers. Now, if you are new here, please do consider subscribing to our YouTube channel. We cover A-level maths and also A-level further maths, and we will be releasing Set A Paper 2 very shortly. And then finally here, before we jump into today's video here, if you are looking for either more A-level maths or A-level further maths revision, please do check out our website, AJMaths.co.uk. We have worksheets, revision videos, and also predicted, or as you can see here, mock exam papers. Okay? But other than that, I am waffling a little bit here, so let's not waste any more time then, and let's just get started with question 1. So let's just get started here then with question 1. Now, as we can see then for question 1 here, we're given that y is equal to the natural logarithm of 3 plus 2x. And for the first part of this question, part A, all we want to do then is find in its simplest form the third derivative of y here, okay? And as we can see then, 3 marks for this here, all things considered, is pretty generous. So let's just scroll down then and have a go at part A. So for part A then, all we want to do here, right, is just find the third derivative. So if we've got y, so y here is equal to ln of 3 plus 2x. Well, what we need to do here then is find the first derivative, dy by dx. So dy by dx here, nice and straightforward then, is simply 2 over 3 plus 2x. So 2 all over 3 plus 2x. Okay. We now need the second derivative here. So that's d squared y over dx squared. Now, for the second derivative here then, as we can see, right, we have a quotient of functions, so we now need to use the quotient rule here. So what would this be then? This would be u is equal to 2. V is my denominator of 3 plus 2x. Like so. U prime here is just 0, and then v prime is simply 2. Okay? Apply the quotient rule here then. And what do we obtain? So it's v, which is this here, times u prime, so that's just 0, minus then 2 times 2, which is 4, so get minus 4, all over v squared. Okay, so that is 3 plus 2x all squared. Like so there. Okay, so this here then is the second derivative. And then finally, we can find the third derivative here. So again, all we need to do is differentiate here with respect to x. So again, we now need to use the quotient rule here. So this time round, u is minus 4, meaning u prime again is 0, and v here is 3 plus 2x all squared. Okay. Now in that case, then v prime here, this requires the use of the chain rule then. So I get 2 times by my derivative here. So, well, the derivative of the inside of the bracket, which is 2. So 2 times 2 is 4. Get 4 there times 3 plus 2x. Don't forget to reduce the power by 1 here. Okay, so we obtain the following there for v prime. So let's just put all this together here then, applying the quotient rule. So again, what do I get here? So it's v times u prime, which again is just 0. We then get minus, so minus 4 times this here. So minus 4 times this here. That is positive, right? So what I get here then is 16 lots. So 16 lots of 3 plus 2x. Like so. And this here then is all over v squared. So v here is 3 plus 2x all squared. So v squared then is 3 plus 2x all squared raised to the power of 2. So altogether here then, for my denominator, you get 3 plus 2x to the power of 4. But what I can do here then is simplify this, right? As the question asks for. Let's just scroll up here. It asks for it in its simplest form. So if I just simplify this here, the third derivative then of y is equal to, so what I can do here then is cancel this factor and reduce that power by 1. So what I get here then is 16 all over 3 plus 2x all to the power of 3 there. Okay, so there we have it then. That gives us the solution to part A. Now for part B then, let's just quickly scroll up here and read the question, or this part of the question anyway. It just says, hence determine the Maclaurin series expansion of ln for 3 plus 2x. So just notice here, that's the exact same as what we was given for y then, in ascending powers of x up to and including the term in x cubed, given each coefficient in its simplest form. So part B here, this is just simply an application of the Maclaurin series expansion. Okay. Now what I require here then is y when x equals 0. I also require dy by dx when x equals 0. And the same is true for the second derivative and also the third derivative. So we've done a lot of the kind of legwork here for this question, right? We found all of the derivatives. So all we need to do here now is evaluate each one when x equals 0. Okay. So y here when x equals 0. So y when x equals 0 here. Don't forget then, y is equal to ln of 3 plus 2x. So if x is 0, y is equal to ln 3 there. Hopefully nice and straightforward. Let's just do the same now for dy by dx here. So dy by dx when x equals 0. So what do we get here? Well, if x equals 0, I get 2 over 3. We get 2 over 3 there. Doing the same now for the second derivative here. So again, just substitute x equals 0 into this expression here. So I get minus 4 all over 3 squared. So that is minus 4 over 9. And then finally here, for the third derivative, that's d cubed y over dx cubed. What do we get here then? So again, just substitute x equals 0 into this expression here. So I get 16 over 3 cubed, which is 16 over 27 there. Okay. Well, in that case then, what I get here is that ln of 3 plus 2x is approximately, so what I'm doing here then is using Maclaurin series expansion given in your formula book. So this is y when x equals 0, so that's ln 3 on my first term. So we get ln 3 there. Now for the second term here, that's going to be dy by dx when x equals 0 times by x. So what I get here then, if I just scroll up, is 2 over 3 times by x. We get plus 2 over 3 times by x there. Okay. Now for the next term then, this is the second derivative. Oops, I also forgot the correct notation here, so apologies about that. And x equals 0. And same again here for the third derivative. So apologies for that there. Like so. So yeah, so the second derivative here, when x equals 0, is minus 4 over 9. And what I do here then, so let me just write this down in full. So this would be minus 4 over 9 times by them. So we times this here by x squared. So x squared over 2 factorial. Okay. I'll simplify that in a moment, so don't worry about that for now. And then finally, for the very last term here, what do we get then? So I've got 16 over 27. So 16 over 27. And I times that here, as you might guess then, by x cubed over 3 factorial. So x cubed over 3 factorial. Okay. This just keeps going on, but we're only concerned about going up to the term in x cubed. So that's absolutely fine here. So to finish with then, let's just simplify here. So we can't do anything with ln 3. So we just leave that as it is. We can't do anything with the second term here. So that's just plus 2 over 3x there. Again, we can't do anything with that. Now, minus 4 over 9 times x squared over 2 factorial. This would simplify here to give us minus 2 over 9 x squared. So minus 2 over 9 x squared. And then finally here for the very last term, or the term in x cubed here, 16 over 27 times x cubed over 3 factorial. This just simplifies here to give us 8 over 81. So 8 over 81 x cubed there. Okay, again, this just keeps going on and on. We're only concerned about going up to the term in x cubed there. Okay, so there we have it then. That gives us the solution to part B. Now for part C then, let's just scroll up here. It just says, hence write down the Maclaurin series expansion of ln of 3 minus 2x. So just notice here then, that is very, very similar to what we had in part B. The only difference now is it's 3 minus 2x as opposed to 3 plus 2x in ascending powers of x up to and including the term in x cubed. So it is almost identical to part B here. So the fact that this question here, or this part of the question, is only 1 mark, that would suggest to me here that there isn't really too much work to this part of the question, right? So for part C here, let's just scroll down then. What you need to recognize here then is that for ln of 3 minus 2x here, this will be approximately then, so it's going to be very, very similar to what we had here. The only difference now is the odd terms here, or the odd powers of x, I should say. So that would be this term here, the next one would be x to the 5, and x to the 7, so on and so on. Those terms, the sign in front changes. So if it's negative here, it becomes a plus, so this is plus 2 over 3, it will be now minus 2 over 3. Same again here, this is plus 8 over 81, it now becomes minus 8 over 81. And that's all that happens here. Everything else remains the same. So if we put that all together here then, what we get is ln 3. This now becomes negative, so minus 2 over 3x, like so. This here doesn't change, so minus 2 over 9 x squared, like so. And this here then changes to negative again because it's an odd power of x here. So we get minus a over 81 there. Okay. Again, this will just keep going on and on. We're only concerned about going up to the term in x cubed there. So that's absolutely fine there for part C. And then finally for part D here, the very last part of this question. What does it want us to do here? So it just says using your answers to parts B and C, determine the first two non-zero terms in ascending powers of x for the Maclaurin series expansion of the following. So let's quickly erase all this here, just so it hopefully doesn't cause confusion. Okay, that's apparently not going to work. Try again. That works. There we go. I'm just going to quickly get rid of all this here. We'll try anyway. That one's not going to work. I'll quickly erase that in a second. Same again. Last one here, and then quickly get rid of that and that. Okay, so what I want to do here then is find the Maclaurin series expansion, or the first two non-zero terms anyway, in ascending powers of x for this Maclaurin series expansion here. So ln of 3 plus 2x of, well, let me try and read that again. Ln of 3 plus 2x over 3 minus 2x. There we go. Maths is hard. So just notice here then what we've got is 3 plus 2x, which is what we had in part B, right? Ln of 3 plus 2x. And in part C, we had ln of 3 minus 2x. So if I just scroll down here then for part D, I've got ln of 3 plus 2x over 3 minus 2x. Okay. Now, by the laws of logarithms here, we can write this as ln of 3 plus 2x minus ln of 3 minus 2x. Now, we know then the Maclaurin series expansion for both of these individual terms here, right? This one here, we did that in part B, and this one here, we just did that in part C. So all I need to do here then is write this as a difference of the Maclaurin series expansions, right? So let's just do that underneath here. So ln of 3 plus 2x, that's what we had in part B here. So I'll put these in two different brackets then. So I've got ln 3. So ln 3 plus 2 over 3x minus 2 over 9x squared. And then finally 8 over 81 x cubed. So 8 over 81 x cubed there, like so. And we now subtract this Maclaurin series expansion here, which is what we had in part C. So again, I've got ln 3 minus then 2 over 3x here, like so, minus 2 over 9x squared. And then finally here, minus 8 over 81 x cubed. Like so there, okay? And now, if we just actually evaluate this difference here, well, ln 3 minus ln 3, they just cancel. I've got 2 over 3x minus 2 over 3x. So 2 over 3x minus 2 over 3x, that is just the same as 2 over 3x plus 2 over 3x, which gives us 4 over 3x there, like so. I've got minus 2 over 9x squared minus 2 over 9x squared. So these two terms here just cancel as well. And then finally, 8 over 81 x cubed minus a over 81 x cubed. Again, we can just add these two terms together. And if we do that here, then what we get is 16. So plus 16 over 81 x cubed there. Okay. And just notice here then, this gives us the first two non-zero terms in ascending powers of x for the Maclaurin series expansion of ln of 3 plus 2x over 3 minus 2x there. Okay. And there we have it then. So that gives us the solution to part D and the solution to question 1. So moving on to the next question here then, let's just have a go at question 2. So as we can see then for question 2 here, what we've got here is figure 1. And figure 1 shows a sketch of the curve with this equation here. So y equals 2 minus sin x. So we can see straight away then that this question here will involve hyperbolic functions. So let's just go down here. We're then told that the curve crosses the x-axis at the point A. So that's this point here. And at this point here, hopefully it's obvious that y is equal to 0. So for part A then, as we can see here, all we want to do is find the exact coordinates of the point A. So all I need here then is the x-coordinate for the point of intersection. And to obtain that, all I need to do here is replace y with 0 in this equation here, and then just solve for x. So if we do that underneath here, for part A then, as we just said, right, 2 minus sin x is equal to 0. Let's just add sin x to both sides here. So sin x is equal to 2. Now, all we want here, right, is just x. So I want x here on the left-hand side. And so just obtain then x on the left-hand side here, I just take r sin of both sides. So x is equal to r sin of 2. Okay. Now just be very, very careful here. The question wants the exact coordinates of the point A. So obviously I can't just give the x coordinate as this here. What we need to do then is use our formula book and give this as a natural logarithm. Okay. So using our formula book here then, what we obtain here is ln of, I get 2 because it's r sin of 2 here. So ln of 2 plus the square root then, we get 2 squared plus 1. Okay, simplify the inside of the bracket here. What we get then is ln of 2 plus the square root of 5. Okay, and this here then is the x coordinate for the points of intersection here. So therefore then, let's just do this at the bottom here. The coordinates for A here are given as, so what do we get here then? So my x coordinate is this here. I get ln of 2 plus root 5 here, like so. And then obviously for the y coordinate here, that's just 0, right? And there we have it then. So the first 2 marks there in the bag, hopefully nice and easy. Now for the second part of the question here, what we're told then is the finite region R bounded by the curve and the coordinate axes is shown shaded in figure 1. Okay, and we can see that here on our diagram. We're then told that the region R is rotated through 2 pi radians about the x-axis. And the question here then wants us to use calculus to find the volume of the solid generator, giving your answer to 3 significant figures. So let's just scroll down here. So this is for part B here. So obviously part B here then is based on volumes of revolution. And because we're rotating here about the x-axis then, the formula that we require here is the following. So V then, the volume here is equal to pi. So pi here times the integral then of y squared with respect to x here. Okay. So y here, let's just make a note then. Y is equal to 2 minus sine x. Okay. And my limits here then would be from 0 to my x coordinate here for the point of intersection, right? We're integrating from here to here. Okay. So the x coordinate then for the point A is what we obtained here in pi A, right? You can see how the structure of this question is intended to help you. So my upper limit then is it's going to be ln of 2 plus root 5 there. Okay, like so. So y squared here then, let's just write this underneath here. So V, the volume, is equal to pi times the integral here. So again, this is from 0 to ln of 2 plus root 5. I don't have a lot of room here. Like so. Now y squared then would be 2 minus sine x all squared. So I've got 2 minus sine x all squared. And we're integrating here then with respect to x. Okay. Now what I would do here is replace sine x and give it as its exponential definition. Okay. I just personally think it's a little bit easier to work with here. So what I've got here then, let me just do it to the right, is the integral then, or pi times the integral here of, again, from 0 to ln of 2 plus root 5. It does get a little bit repetitive writing this each and every time, but it is necessary. So I've got 2 minus then a half times e to the x minus e to the minus x there. Okay. And all of this here is squared. And we're integrating here with respect to x. So all I've got to do here then is expand this bracket out here. So 2 minus a half e to the x minus e to the minus x all squared. So just expand these double brackets here. And we're then going to integrate with respect to x. So I won't go into a massive amount of detail here in terms of expanding these brackets, right? I don't want these questions to go on forever and ever. But what you should get here then, and let me just do this to the left here, sorry, just so there is a little bit more room then, is pi times by the integral here from 0 to ln of 2 plus root 5. So if you expand these brackets out here correctly, then what you should obtain is, so we get 4 minus 2 times e to the x minus e to the minus x there, like so. And then finally get 1 over 4. So 1 over 4 e to the 2x. So e to the 2x plus e to the minus 2x. And then finally minus 2 here. Okay, like so there. And again, don't forget here that we're integrating with respect to x here. Okay. And all I need to do here now is just go term by term here, integrating with respect to x. So again, I won't go into a massive amount of detail here as to how you should kind of evaluate this integral here. I'm hoping this is pretty straightforward, right? We're basically just integrating exponential functions. So again, this is just basic A-level maths integration. But what you should get here then is pi times by, so 4 here, that integrates to give us 4x. For the next term here then, this just integrates to give us, so this doesn't change, I just get minus 2 times e to the x, like so. Obviously, just be careful here with the second term, right? Once you integrate this here, so this would be minus 2 times e to the x. That just integrates to give us minus 2 times e to the x. This term here, that would be plus e to the minus x there, like so. Just be very, very careful with your signs here. And then for this one here, I get 1 over 4 again here on the outside. Now inside the bracket, this is going to be 1 over 2 e to the 2x. 1 over 2 e to the 2x. For the middle term here, again, just be careful with your signs. I get minus a half e to the minus 2x. And then finally, minus 2x here. Okay. Like so there. Don't forget the limits of integration here. So from 0 to ln of 2 plus root 5 here. Okay. And at this point here then, either just use a calculator or just evaluate this by hand. Either way, what you should get here then, 1 times by pi is 7.37 there. Okay. And that is 2 free significant figures there. Okay. Again, I don't want to go into too much detail here in terms of limits, right? Just substitute in the upper limit, subtract the lower limit, and what you should get here then, 1 times by pi is 7.37 there. Okay. So what that gives us here then is by using calculus, the volume of the solid generated, right? Once we rotate through 2 pi radians about the x-axis, okay? And that is for this region R here, okay? But there we have it then. That is the solution to part B and the solution to question 2. So for the next question here, then we have question 3. So as we can see then for question 3 here, we have the curve C, which has this polar equation. We're then told that the point P lies on C such that the tangent to C at P is perpendicular to the initial line. We're then given that O is the pole, and all we want to do here is find the exact length OP. So to get us started here then, let's just note then that R here is equal to 1 plus 2 cos theta. Okay. Now, what's important here then, in the context of the question here, what we're given basically, is that we're told that it's perpendicular to the initial line. Now that's important then, because what that tells us here is that at some point in this question here, we require dy by d theta, and we set dy by d theta equal to 0. Okay. So you should be aware then that y here, so y is equal to r sine theta. So r then is 1 plus 2 cos theta. So if we just put that all together here, then we obtain that r times sine theta here is just sine theta times 1 plus 2 cos theta. Okay. If we just expand this out here, then we get sine theta, and then sine theta times 2 cos theta, that just gives us 2 sine theta cos theta. Like so there. Okay. Now 2 sine theta cos theta, we can just rewrite that as, I've got sine theta, and then 2 sine theta cos theta. As we just said then, we can rewrite this here as sine of 2 theta. Okay. And as we said then at the beginning of this question here, we require dy by d theta is equal to 0. Okay. So let's just differentiate y here with respect to theta and set that equal to 0. So dy by d theta here is equal to the following. So nice and straightforward then, just go term by term here. So sine theta differentiates to give us cos theta, and then sine of 2 theta, that just gives us 2 cos 2 theta. Okay. Now, what I do here is I set this equal to 0, but trying to solve this here isn't the easiest. So what I need to do here is use them. I'll just make a note here at the top then. So we're going to use cos 2 theta is identical to 2 cos squared theta minus 1. Okay. So we can rewrite this here then as cos theta. So cos theta plus 2 lots of this here. So 2 lots of 2 cos squared theta. That's 4 cos squared theta. Like so. And then 2 times minus 1. That just gives us minus 2 here. Okay. And again, this here is all equal to 0. Now, again, all I want to do here is just solve this equation. And what I've got here now is a quadratic equation. So it's much easier to solve, right? Now, unfortunately then, this quadratic equation here does not factorize, so we need to use a different method here. And obviously it just makes sense then to use the quadratic formula here. So using the quadratic formula here then, cos theta is equal to get -1 makes things a little bit easier here. Let's just write this as 4 cos squared theta plus cos theta minus 2 is equal to 0. So just so we can see then A, B, and C here, just makes life a little bit easier. We get -1 plus or minus them. So plus or minus here, the square root here of, so I get B squared, so that's 1, minus then 4AC, so 4 times A, which is 4, times C, which is -2, like so. And this here then is all over 2A, that's 2 times 4, which would give us 8 there, right, when we simplify. So let's just simplify here then. What do we get? We get -1. So -1 plus or minus them, the square root here, the 1 minus 4 times -2. So this here is, so 4 times 4 is 16, times that by -2, that's -32. 1 minus -32, that gives me a square root there of 33. Okay, and this here then is all over A. Okay. Now, because theta here is between 0 and pi over 2, we just take the positive solution here. Okay. So as theta then is between 0 and pi over 2 here, what that means here then is we just take the positive solution. So therefore, in that case then, OP here, so what that means here then is OP is equal to, so all I'm going to do here then is just substitute this value here of cos theta into R, right? So OP then is 1 plus 2 lots of this here, where I've took the positive solution. So if I just make a note here underneath, cos theta is equal to -1 plus root 33 over 8 there. Okay, so 1 plus 2 lots of -1 plus root 33 all over 8 there, like so. If we just simplify this here, then what would that give me? So I'm going to get 2 lots of this here. So that would just be, it's going to be plus, I get -1 plus root 33 all over 4. Like so, like this bit here. So -1 plus root 33 over 4. I appreciate I'm not explaining this very well here at this final part, but stay along with me. We're nearly there. If I just get this over a common denominator here, then what do I get? So over a common denominator here, I get 4 plus -1 plus root 33 all over 4. And that just simplifies here then to give us 3 plus root 33 all over 4 there. Okay. And there we have it then. This here is the length of OP here. Okay. And there we have it then. So that gives us the solution here to question 3. So moving on to the next question here then, where we now have question 4. So as we can see then for question 4 here, we have the matrix A, which is given as follows. So A here is a 3x3 matrix, and we're told that K is a real constant. Now for the first part of this question, part A, all we want to do then is find the value of K for which the matrix A is singular. So let's just scroll down here. So if the matrix A is singular here, what that's telling us then is that the determinant of the matrix A, so det A here, is equal to 0. Okay? So all I need to do here then is find the determinant of this 3x3 matrix here, set it equal to 0, and then solve for K. And to do that here then, let's just expand along the top row. So what I'm going to get here is k times by. So what I do here is I cross the top row off and then this column here. And as we can see then, we get left with this 2 by 2 determinant here. So 1k, 1, and 4. So like we just said then, 1k, 1, and 4. If we just keep going along the top row then, now when we get to this element here, it's just 0, and anything times by 0 is just 0. So that just makes life a little bit easier here. And then for the final element, 1 times by, so what I do here, across this row and this column. And as you can see then, we get left with this 2 by 2 determinant here. So minus 1, 1, 3, and 1 there. Okay. So we get plus 1 lot of our 2 by 2 determinant here of minus 1, 1, 3, and 1 there. Okay. And this here then is equal to 0. So all we need to do here now is evaluate these 2 by 2 determinants, simplify, set it equal to 0, and then solve for k, right? So this 2 by 2 determinant here is 1 times 4 minus k times 1. I've got a k times by 4 minus k. Doing the same here then, for this 2 by 2 determinant, we get minus 1 times 1, which is just minus 1 times 3. So I get minus 1 minus 3, which is minus 4, times it by 1, and we get minus 4 there. And this here then is equal to 0. So let's just expand here and simplify. So I get minus k squared plus 4k minus 4 is equal to 0, right? And what we want to do here is solve for k. So to make life a little bit easier here, let's just times through by minus 1. We get k squared minus 4k plus 4 is equal to 0, right? And hopefully what you recognize here is this is k minus 2 all squared, okay? And this here then is equal to 0. And this just gives us k is equal to 2 here, okay? So this value here, k equals 2. This is the value of k for which the matrix A is singular, okay? So there we have it then. That gets us the first 3 marks of question 4. Now for part B then, we're given that the matrix A is non-singular. And for part B then, we want to find the inverse of the matrix A in terms of k. Now, for 1 extra mark here, part B is a lot more work. So do take your time here and just be very, very cautious as you work through part B. So to get us started here, we begin with the matrix of minus. So this is the matrix M. And M here is basically a massive 3 by 3, not determinant, but a 3 by 3 matrix of the individual 2 by 2 determinants. So there we go, we got the right way around. So how do we evaluate that? Well, just go back to the original matrix here, the matrix A, and we expand then basically across each row here. Okay, so for the first one then, we cross off this row and this column. And as you can see then, I get left with this 2 by 2 matrix here, 1k, 1, 4. So my first 2 by 2 determinant here, as we just said then, is 1k, 1, and 4. Okay, for the next one along here, again, go back to the original matrix, we cross off this row and this column. And we get left with minus 1, k, 3, and 4. So minus 1, k, 3, and 4. Okay. For the final element then, along this row here, so this would give us our final 2 by 2 determinant along the top row. We cross off this row and this column. And we get left with minus 1, 1, 3, and 1 there. So like we just said then, we get this 2 by 2 determinant here. So we get minus 1, 1, 3, and 1 there. Okay. So that's the top row complete. I'm not going to go through each individual 2 by 2 determinant here, just because it would take quite a bit of time, right? And these questions do take enough time anyway. So I'll do the final one here or my final example here as the first one along the middle row, and I'll just give you the remaining 2 by 2 determinants to evaluate. So we cross off this row here and cross off this column. And as you can see then, I cross off this row here and this column here. It doesn't do a very good job of it, but there we go. I get left with 0, 1, 1, and 4. Okay. Like we just said then, we get 0, 1, 1, and 4. Okay. So to finish with then, let me just give you the remaining 2 by 2 determinants here. We get k, 1, 3, and 4. Then for the final one here along the middle row, we get k, 0, 3, and 1. Okay. And now for the final row here, what do we get then? To get 0, 1, 1, and k. For the middle one here, we get k, 1, minus 1, and k. And then finally here, for the very last 2 by 2 determinant here, we get k, 0, minus 1, and 1 there. Okay, so this here then is the matrix of minus. Now, like you can see, there's a lot of work going on here. What I now need to do is actually evaluate each 2 by 2 determinant. Okay, so like I said, there's a lot of work involved with these types of questions. So just take your time here. There's no rush, right? We don't want to make a silly mistake. So what I get here then is the following. So if we evaluate this 2 by 2 determinant here, that's 1 times 4, which is 4, minus k times 1. We get 4 minus k there. Like so. Let's just keep going here. So again, I don't want to go into too much detail here evaluating these 2 by 2 determinants. It should be pretty straightforward. So for the next one here, I get minus 4, minus 3k. The next one here, that's minus 4. For this one here, I get minus 1. That's this 2 by 2 determinant. For the next one here, I get 4k minus 3. And then for this one here along the middle row, we get k. And now for the final row then, minus 1, k squared plus 1. And then finally here, k in the bottom right corner. Okay. So we're progressing quite nicely here. And we just need to keep continuing now with this process here for finding the inverse of a 3 by 3 matrix. So what I need now then is what we call the matrix of cofactors. Okay. And we use C here to represent the matrix of cofactors. So for the matrix of cofactors here, the best way to remember this is to start then, and this is for a 3 by 3 matrix, by the way. So our top left element here is always positive. And what we do now is we alternate. So it's plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay. So basically, wherever I have a minus here, it's just kind of this diamond here. You want to think of it like that. So these 4 here will just change to the opposite sign. Everything else just stays the same. So if I do that here, so like we just said, right, the 4 minus k just stays as it is. That doesn't change. So that's 4 minus k. This one here now will change sign, right, because it's minus. So minus 4 minus 3k, that is just 3k plus 4. This one here just stays as it is. So minus 4 there. This one here changes sign. So instead of minus 1, it's now just 1. This one here stays the same. So 4k minus 3. This one here will change sign. So that's now minus k. This one here stays the same, minus 1. This one here changes sign. So minus k squared, minus 1. And then finally, this one here stays the same. Okay, so this here is the matrix of cofactors. And what we now need to do here is find the transpose of the matrix of cofactors. So that's C then to the power of t here. So C to the power of t here, this is just the matrix of cofactors transposed. So when we transpose a matrix here, the first row becomes the first column. I get 4 minus k, 3k plus 4, then minus 4 here. The second row becomes the second column here. So I get 1, 4k minus 3, and then finally minus k here. And now the final row becomes the final column. So I get -1. We then get minus k squared, -1, and then finally here, we get k in the bottom right corner, like so there. And at this point here, we're pretty much done now with the inverse of the matrix A in terms of k. All we now need here then, for the inverse of the matrix A, is 1 over the determinant of A, which we did actually evaluate in part A here. Let's just find that. That was this here. So it's going to be 1 over that. So 1 over the determinant of the matrix A here, which was minus k squared. And we also had minus 4k plus 4. Let me just quickly double check that. Plus 4k. Oh, which way is that? Plus 4k? Is it plus 4k? Let me just quickly double check that. So minus k squared. Yeah, plus 4k. So just be very, very careful there. Don't make a mistake like that. So minus k squared plus 4k. Is that minus 4 then? Yeah, minus 4. I'm getting the signs the wrong way around. Let's try again. So minus 4 there. There we go. See, like I said, very, very easy to make a mistake here. So 1 all over minus k squared plus 4k minus 4. Let's just quickly double check that one more time. So minus k squared plus 4k minus 4. Yeah, perfect. Good stuff. And what I now do here is we times this by the transpose then of the matrix C. So that's 4 minus k, 1 minus 1, 3k plus 4, 4k minus 3, minus k squared, minus 1, minus 4, minus k, and then finally k here. Okay. And this here then is the inverse of the matrix A in terms of k there. And as you can see then, that is 4 marks for all of part B. It is a lot of work really just for 4 marks, but nothing particularly too challenging there. Like I said, more than anything, it's just very, very easy to make a mistake. Okay. But there we have it then. So this here is what you should get for part B. And then finally to finish with here, right, because we're not even finished just yet, we have a proof by induction to finish with. So we want to prove then by induction that for all positive integers n, m to the power of n, so what have I missed here? The matrix M is given as follows. So m to the power of n is equal to this here. Okay. There shouldn't be a power of n there. My apologies. That shouldn't be there. So just ignore that. So m to the n is equal to n plus 1, n minus n, and 1 minus n there. And as we can see, 4 marks for this. It's pretty standard stuff, right? Just a basic proof by induction. More than anything, again, it's just a bit of a tedious process for proof by induction, but nothing too challenging, right? So for part C then, we just start here with the base case. So for the base case here, I'm just going to let n equal 1. So we let n equal 1 here. Okay. So on the left-hand side here, what do I get here then? So on the left-hand side, that's m to the power of 1. So m to the power of 1 here is just 2, 1, minus 1, and 0. That's just 2, 1, minus 1, and 0 there, like so. And for the right-hand side here, what do we get then? So that's going to be 1 plus 1, which is 2, 1, minus 1, and 1, minus 1 there. So altogether here on the right-hand side, what we get then is we get 1 plus 1, we get 1, minus 1, and 1, minus 1 there. And if we simplify this here, we get 2, 1, minus 1, and 0. And just notice here then, the left-hand side is equal to the right-hand side. So therefore, the left-hand side is equal to the right-hand side. Okay. And it holds for n equals 1. Or you could say it's true for n equals 1. So true for n equals 1. So that's the first step complete there. Now for the next step here, this is what we call the assumption step. So for my assumption here, let's just write this down in full here. So for the assumption step here, what I'm going to do here then is assume that this is true for n equals k. So assume true for n equals k. Okay, so if this is true for n equals k, then what I get here is the left-hand side, that was 2, 1, minus 1, and 0, to the power of n here. That's to the power of k now. This here then is equal to the right-hand side, and just replace any n's with k. So I get k plus 1. We get k minus k, and then 1 minus k there. Like so. Okay. So that's all we need there for the assumption step, right? The assumption step is basically setting us up for the inductive step, which is the next step here. So, as we just said, then we now have the inductive step. So for the inductive step here then, what do we now do? So what I'm going to do here is let n be equal to k plus 1. So if n is equal to k plus 1 here, what we get then is 2, 1, minus 1, and 0 to the power of k plus 1 here. Okay. And this is just the same then as 2, 1, minus 1, and 0 to the power of k times by itself again. So 2, 1, minus 1, and 0. This is just basic rules here of indices, right? So this here from our assumption step is k plus 1, k, minus k, and 1 minus k. So let's just replace that then. So k plus 1, k, minus k, and 1 minus k there. And we times it by this matrix here. So 2, 1, minus 1, and 0 there. Okay. So let's just keep going here and let's just actually evaluate this product here then. So if we expand these two 2x2 matrices together here, what do we get then? I've got this row here times by this column. So I get 2k plus 2 minus k. So 2k plus 2 minus k there. I then have this row times by this column here. So I just get one lot of k plus 1 here. Like so. I then have this row times by this column. I get minus 2k minus one lot of 1 minus k there. So just be very, very careful with your signs here. So minus 2k times by minus one lot of 1 minus k here. So that's plus k minus 1 there, like so. And then finally here, this row times by this column. Okay, so minus k times 1 is minus k. Obviously 1 minus k times 0 is just 0, right? And we get this here. Now, if you just go back to the question here, right? And if we just think about this for a moment, what I want to do here is replace n with k plus 1. I should get k plus 2, k plus 1, minus k plus 1 here, and 1 minus k plus 1. So if I just simplify this here, what do we actually get then? So simplifying this here, what I get then is the following. So I get k, so 2k minus k is just k plus 2 there. So k plus 2. I get k plus 1 here, the top right element, minus 2k plus k, that's minus k, minus 1 there, and then finally minus k here. And just notice then, what I can do here is write this as the following. So this is k plus 1 plus 1. This here is just k plus 1. We can't do anything with that. Minus then k plus 1, exactly as we said, right? And then finally here, this is 1 minus k plus 1. Like so there. And therefore, what we've proved here is that the matrix equation is true when n equals k plus 1. So the matrix equation is true when n equals k plus 1. Okay. So we're pretty much complete now with our proof by induction here. All we now need to do, there we go. This question's too long. All we now need to do here is just give our conclusion. So for the conclusion here, or the conclusion step, whatever you prefer to kind of call this here, then I'm just saying basically something along the following lines. So if true for n equals k, then it's shown to be true for n equals k plus 1. So then true for n equals k plus 1. And because it's true for n equals 1, and because it's true for n equals 1, then it's also true for all n belonging to the set of positive integers here by mathematical induction. So then also true here for all n belonging to the set of positive integers here, like so, by induction. Okay, something along these lines here is what we need to finish with for our proof by induction. Okay, there's supposed to be an exclamation mark. There we go. Perfect. So that question is too long. I do always find normally the matrices questions are a little bit lengthy. There is normally a lot of work, but mathematically nothing too challenging there. But hopefully, the proofs here, or the proof by induction, and part B and part A here, just make things a little bit easier and help illustrate how you would work through a question such as this one. Okay, so there we have it then. That gives us the solution here to question 4. So moving on to the next question here then, where we have question 5. So for question 5 here, we're given that y is equal to arcsine x for x between -1 and 1. Now, for part A of this question here, all we want to show then is that dy by dx is equal to the following here. So this is just proving one of our standard results here. And as we're told underneath, right, we can assume the derivative of sine x here without proof. So let's just scroll down here. So this is for part A. Okay. So we're given in the question then that y here is equal to arcsine x. Okay. Now what we want here then is dy by dx, right? So what I want to do here is get rid of the arcsine x on the right-hand side. We just want x here, okay? So to do that, I just take sine of both sides here. On the left-hand side, we get sine y. And on the right-hand side here then, sine of arcsine of x here is just simply x, okay? And at this point here now, what we're going to do is differentiate implicitly, okay? So if we differentiate implicitly here then, what we get on the left-hand side is cos y. So we get cos y dy by dx is equal to 1, okay? Now we just want dy by dx, right? So all I need to do here is just divide both sides by cos y. So I'll do it underneath here. So therefore, dy by dx here is equal to 1 all over cos y. Okay? Now, obviously we're not done here because we want this result, 1 over the square root of 1 minus x squared. I've got 1 over cos y here. So at this point here, what we're now going to do is use one of our trigonometric identities, right? We're going to use here. So we're going to use then cos squared y is equal to 1 minus sine squared y. Okay? So what I can do here then is rewrite dy by dx here as 1 all over the square root then. So cos y here, just take the square root of both sides here then, that is the square root of 1 minus sine squared y. So 1 minus sine squared y here, like so. And we know then that sine y here is equal to x. If we just square that then, sine squared y is equal to x squared. So this just gives us here 1 all over the square root here of 1 minus x squared, exactly as we require. Okay, so as required there, and part A complete. So hopefully nothing too challenging there for part A. Now for part B then, this here is a little bit more difficult. So it says hence or otherwise prove that 1 minus x squared times the second derivative minus x times the first derivative is equal to 0. So let's scroll down here. This is for part B, right? So what we need here then is the second derivative. So let me just note here the first derivative. So dy by dx here is equal to 1 all over the square root of 1 minus x squared. Okay. So for the second derivative here, right, we do require the use of the quotient rule. So let's make a note here that u is equal to 1. In that case, then u prime is simply 0. V here, that is my denominator. So that is 1 minus x squared all to the power of a half here because it's the square root of 1 minus x squared. We've got 1 minus x squared all to the power of a half here. And then for v prime, well, this would require the use of the chain rule here. So the derivative of the inside of the bracket here is minus 2x. So if I times it by half, then I just get minus x here on the outside. And don't forget as well here that we need to reduce this power by 1. To get 1 minus x squared all to the power then of minus 1 over 2. Okay, so by the quotient rule here then, the second derivative, so the second derivative here is equal to, so I get v times u prime, so that's just 0, right? So I get 0 minus them. So what do I get here? So I get v prime times u. So that's minus x times 1 minus x squared all to the power of minus a half times 1. So like we just said, then we get minus x times 1 minus x squared all to the power here of minus a half. Okay, like so. And this here then is all over v squared. Now v then is 1 minus x squared all to the power of a half here. So if we raise all of this here to the power of 2, 1 over 2 times 2 is just 1. So for my denominator here then, you simply get 1 minus x squared there. Okay. I didn't particularly need to write that in brackets, but I'll just leave it as it is anyway. So let's just simplify the numerator here. So minus x here, this just all becomes positive here then for the numerator. So I get x times by 1 minus x squared, all to the power then of minus 1 over 2. And this here is all over 1 minus x squared. Okay, like so there. Now using the laws of indices here, we can just rewrite this ever so slightly. I can rewrite this here then as x all over, so this is x here all over 1 minus x squared times 1 minus x squared here. So what I've got here is x all over the square root of 1 minus x squared times 1 minus x squared there. Okay. Now, if we just go back to part B then of this question here, what we have then is 1 minus x squared times the second derivative here. So what I've got then is this here for the second derivative. That's d squared y over the x squared, like so. So what happens here then if we times this by 1 minus x squared? So therefore 1 minus x squared times by the second derivative here. What does that give us then? To get 1 minus x squared times by this here, or times by this here, which is x all over the square root then of 1 minus x squared times by 1 minus x squared, like so. And just notice here then, this would cancel with this here. So what I get left with then is x over the square root then of 1 minus x squared. And just notice here that this result is very, very similar to what we obtained then in part A, right? In part A, we obtained that dy by dx was equal to 1 over the square root of 1 minus x squared. At this point here, we have x all over the square root of 1 minus x squared. So if I write this here as x times by, so x times by 1 over the square root then, so 1 all over the square root of 1 minus x squared here, this is just the same then as x dy by dx, right? This here, this result here, is just dy by dx from part A. So this gives us x dy by dx here. And just notice then, given that this here, 1 minus x squared times the second derivative is simply equal to x dy by dx then, if we subtract that from this here, that would just be 0, right? So therefore, 1 minus x squared times the second derivative here, minus this here, because as we've just proved then, 1 minus x squared times the second derivative is just equal to x times the first derivative. So if we just subtract x times the first derivative from this here, that would just be equal to 0. So minus x dy by dx here, and in that case, this here is equal to 0 as required. Okay, and there we have it then. So hopefully that solution there, my waffling did make sense as we kind of work through the question. As I said, not the easiest parts of the question here, but hopefully my solution here has helped. Okay, so there we have it then. That gives us the solution to question 5. So moving on to the next question here then, let's just have a go at question 6. So getting started with part A then, as we can see here, right, we're given that the modulus or the absolute value of z here is strictly less than 1. And all we want to do for part A then is just write down the sum of the following infinite series. So 1 plus z squared plus z cubed plus so on and so on. Now, hopefully you recognize then straight away that this series here is a geometric series, right? So for part A then, what I've got here is a geometric series. So geo series here, where my first term, A, is equal to 1. My common ratio here is z. Okay, so A equals 1 and z, R here, our common ratio is z. Okay. Now, for the sum of the infinite series then, that is the sum to infinity. And don't forget then that the sum to infinity here of a geometric series is given as A over 1 minus R. So in that case here, we get A, which is 1, all over 1 minus R, which is Z. Okay. And there we have it then. So nice and straightforward. That gives us the solution to part A. Now for part B then, what we're given here is that Z is equal to 1 over 3 cos theta plus I sine theta. But it says here then for part B, using your answer to part A and de Moivre's theorem, or otherwise, prove the following. So where do we begin here? So for part B then, where do we begin here? Well, what I've got here is 1. So going up to part A then, I've got 1 plus z squared plus z cubed plus so on and so on. And z here is 1 over 3 cos theta plus I sine theta. So what I've got here then is 1 plus z, which I'll write just here just so you can see then, z is equal to 1 over 3 bracket cos theta plus I sine theta. Okay. So what I've got here then is 1 plus, so 1 over 3 bracket cos theta plus I sine theta. Okay. For the next term here, this would be z squared. So what I've got then is plus, I've got 1 over 3 times by cos theta plus I sine theta all squared. So this is 1 plus z squared. Let's just do one more term here. This is z cubed. So again, I get 1 over 3 cos theta plus I sine theta. And this here then is all cubed. Okay. Now, by Demoivre's theorem then, we can simplify this. So I get 1 plus, so this term here would just be 1 over 3 cos theta plus I sine theta. We can't do anything with that. So 1 over 3 times cos theta plus I sine theta. Now for this one here, using Demoivre's theorem then, well, 1 over 3 squared is 1 over 9. I get plus 1 over 9 times by here. So again, by Demoivre's theorem here, we get cos 2 theta plus I sine 2 theta. So cos 2 theta plus I sine 2 theta. Okay. For the next one here, 1 over 3 all cubed is 1 over 27. Get plus 1 over 27 times by them. Again, by Demoivre's theorem here, we get cos 3 theta plus I sine 3 theta. Okay, like so there. Now at this point here, what we now need to do then is separate the real and imaginary parts here. So let's just separate the real and imaginary parts here. So for the real parts here, then what I get is 1 plus 1 over 3 cos theta plus 1 over 9 cos 2 theta plus 1 over 27 cos 3 theta plus so on and so on. We get 1 plus 1 over 3 cos theta plus 1 over 9 cos 2 theta plus so on and so on, right? That would just keep going on and on. And then for the imaginary part here, so I get plus I times by them. So what I get here is 1 over 3 sine theta. Don't forget we factored out the I here at the front. So 1 over 3 sine theta plus 1 over 9 sine 2 theta. And again, plus so on and so on, right? Like so. So what we're now going to do here is use the fact that the sum here, this infinite series, okay, as we had here in part A, is equal to 1 over 1 minus z, okay? So now use them. So now use 1 plus z squared plus so on and so on is equal to 1 over 1 minus z, where z here, so just to make life a little bit easier here, I'm going to give z in its exponential form. So I get 1 over 3 e to the I theta here. Okay, so rather than writing this here as 1 over 3 cos theta plus I sine theta, I'm giving that as 1 over 3 e to the I theta there. Okay, so what do we have here then? I've got 1 all over 1 minus z is equal to 1 all over then 1 minus 1 over 3 e to the I theta here, right? So this is just 1 minus z, where z is 1 over 3 e to the I theta. Now, if I just times both top and bottom here by 3, that just gives me 3 all over then 3 minus e to the I theta there, like so. And at this point here then, what I now want to do here is times through by the conjugate, okay, the complex conjugate here. Now, if we do that then, I times through here by, and just be very, very careful with this, we times through by 3 minus e to the minus I theta here. So minus I theta, okay, like so. And we do this both top and bottom here. So 3 minus e to the minus I theta there, okay. Unfortunately, I'm going to run out of room here to do this on this page. Let's just scroll down then, which is a little bit annoying because I want this result here. So let me just quickly rewrite this. As I said, very, very annoying, but doesn't really matter too much. So 3 over 3 minus e to the I theta. We times this here by, the complex conjugate then, which is 3 minus e to the power then of minus I theta. So I get 3 minus e to the minus I theta. Same again here then with the denominator of 3 minus e to the minus I theta there. Okay. So if we just expand out here then, both for the numerator and the denominator here, we'll start off with the numerator. It's a little bit easier. So 3 times 3 is just 9. So we get 9 there. And then 3 times minus e to the minus I theta. That just gives us minus 3e. So minus 3e to the power then of minus I theta. Okay. So that's my numerator dealt with. Now for the denominator here, it's a little bit more complex, but nothing too challenging here really. So just expanding these double brackets here then. 3 times 3 is 9. And then get 3 times minus e to the minus I theta. So that's minus 3e to the minus I theta. Minus 3e to the minus I theta. So just be very, very careful here. Just take your time, right? There's no rush here. Minus e to the I theta times 3. Again, I get minus 3e. Just be very, very, very careful here. The power now is positive. So minus 3e to the power now of I theta, like so. And then finally here, minus e to the I theta times minus e to the minus I theta. That just gives us 1. Okay. So what I can do here is simplify. So I've got 9 minus 3e to the minus I theta. We'll deal with that a little bit later on for now. So we'll deal with that a little bit later on, but for now, that's absolutely fine. Or my denominator here, what do we get then? So 9 plus 1 is 10. And now what I'm going to do here is factor out the minus 3. So I get 10 minus 3 times by e to the I theta. So e to the I theta minus e to the minus I theta. Okay. Like so there. Let me just quickly double check I haven't made a mistake here. So 9 minus 3e to the minus I theta, that's absolutely fine. 10, so 9 plus 1 is 10. Minus 3, so I factor out the minus 3 here. That should be a plus there, sorry. So that should be a plus. Perfect. So yeah, just take your time, right? As you can see, I just nearly made a mistake myself. Very, very easy to make a mistake with questions like this. So what I can now do here is replace these exponential forms then with our trig functions here, right? Cos theta and I sine theta. Where appropriate, of course. So 9 minus 3e to the minus I theta then. So this here, this e to the minus I theta is just the same as cos theta minus I sine theta. Okay, so what I've got here is 9 minus 3 lots of cos theta. So cos theta minus I sine theta. Like so. This here then is all over. So this is all over e to the I theta plus e to the minus I theta. So e to the I theta plus e to the minus I theta. This here then is just 2 cos theta. Okay, so again, just be very, very careful here. So I get 10 minus 3 lots of 2 cos theta. Like so. And if we just simplify here then, what do we get? So therefore we get 9 minus 3 cos theta. So 9 minus 3 cos theta here, and then minus 3 times minus I sine theta. That just gives us 3i plus 3i sine theta there. That's the numerator dealt with there. And now for the denominator here, we get 10 minus 6 cos theta there. Okay. And then we're nearly finished here. So to finish with here then, let's just equate the real parts here, because what we had then in part B here was this summation. So 1 plus 1 over 3 cos theta plus 1 over 9 cos 2 theta. This part here is the real part. Okay, so this is the real part here. So let's just equate then the real parts here. And we just make a note of that here. So equate in real parts. Equating the real parts here then. I've got 1 plus 1 over 3 cos theta plus 1 over 9 cos 2 theta plus so on and so on. This here then is equal to, so my real part here is 9 minus 3 cos theta. Get 9 minus 3 cos theta all over then 10 minus 6 cos theta. And just notice here then, this is exactly what we wanted to obtain in part B here. So 9 minus 3 cos theta over 10 minus 6 cos theta there. Okay, exactly as we required. So as required there, and question complete. So well done if you got to the very end here of this question and obtained the correct result. These questions here are never easy, and as you can kind of see from my working here, it is very, very easy to make a mistake. So just take your time, be very, very careful as you work through questions like this. But there we have it then. That gives us the solution here to question 6. So for the penultimate question here, we have question 7 looking at vectors. So for this question here, we have 2 helicopters that are traveling in straight lines in an arbitrarily large open space. Now, as we can see underneath here, we have the vector equations of the straight lines L1 and L2, where lambda and mu are simply scalars. So for the first part of this question here, all we want to do then is determine whether the helicopters are moving in perpendicular directions. So to ascertain here as to whether the helicopters are moving in perpendicular directions, what we need to consider here is the dot product of the 2 direction vectors. Now, if we find that the dot product is equal to 0, then they are moving in perpendicular directions. And if we find that the dot product is not equal to 0, then what that tells us here is they are not moving in perpendicular directions. So nice and straightforward here then for part A. Like we just said, right, all we need to do here is find the dot product of the 2 direction vectors. So we have 2, 4, 3. And we dot that with this vector here, our second direction vector, of 2, 1, 1. Okay, nice and straightforward here then. We get 2 times 2 plus 4 times 1. And then finally, plus 3 times 1. Now, I can see straight away here that this will not be equal to 0, right? I get 4 plus 3, which is equal to 11, which is clearly not equal to 0. So what we say here then is they are not, so the helicopters are not moving in perpendicular directions. So not moving in perp directions here. Okay, that's all we need to say here then for part A. Now for part B then, what do we have here? So we're given that the helicopters intersect at the point A, and all we want to do here then is determine the position vector of A. Now, this is pretty standard stuff, right, for vectors, determining a point of intersection. So for part B here, what do we need to do here? Well, what we want to do here is form a system of equations, right? I know then for L1 here we have 3 plus 2 lambda, minus 2 plus 4 lambda, and 1 plus 3 lambda. And in a similar fashion here then for the line L2, we have 1 plus 2 mu, 0 plus 1 mu, and then finally 2 plus 1 mu. So what I can do here then is equate those and form a system of equations. So like we said, then we get 3 plus 2 lambda is equal to 1 plus 2 mu. We also have minus 2 plus 4 lambda is equal to mu. And then finally here, 1 plus 3 lambda is equal to 2 plus mu. Okay, let's call this equation here equation 1, this equation here equation 2, and then finally this equation here equation 3. Okay, so all we want to do here then is solve this system of equations, right? And the easiest way to do that here is to take equation 2 and substitute equation 2 then into either equation 1 or equation 3. Now, in this situation here, it's probably easiest to substitute this into equation 3, right? Because we've got mu here, and in equation 3 we have 2 plus mu, as opposed to equation 1, which is 2 mu. It's not a massive difference, but just makes things a little bit easier. which is obviously the best thing that we can do here. Maths is already hard. Let's make it that little bit easier, right? So substituting equation 2 here into equation 3. So basically just replacing mu here with mu from equation 2. So if we do that then, I get 1 plus 3 lambda is equal to 2 plus mu, but mu here is 4 lambda minus 2. So 4 lambda minus 2 there. Now clearly 2 minus 2, they just cancel. So I've got 1 plus 3 lambda is equal to 4 lambda. And just solving for lambda here, we obtain that lambda is equal to 1, right? And if we know the value of lambda here, we can now easily solve for mu, right? Just using equation 2 here. So using equation 2 here then, as we can see, right, mu is equal to 4 lambda, so that's 4 lots of 1, which is 4, minus 2, giving us 2 there. Okay, so in that case then, lambda is equal to 1, and mu is equal to 2. Now what I need to verify here then, is that these two solutions, so lambda equals 1 and mu equals 2, do hold for the first equation here, right? Equation 1. So let's just make a note here. So verify for equation 1. So if we do that then, what do we get here? So equation 1, if I just scroll up a little bit, is 3 plus 2 lambda. So that's 3 plus 2 lots of 1. And that is equal to 1 plus 2 lots of 2. Well, 3 plus 2 is 5. 1 plus 4 is also 5. So perfect, right? It holds for equation 1. And therefore, what that tells us here then is that the two lines here do intersect at a point. Okay? So therefore, the lines intersect. So the lines intersect here. We're not done because don't forget then, we do also need the position vector here of A. So to find A then, well, not to find A, but the position vector of A anyway. There's two ways to do this. You can have use L1 here with lambda equals 1, or we can use L2 with mu equals 2. It's completely up to you. Either method is fine, and you'll get the same answer either way. Okay, so if I just use them, so use L1 here and lambda equals 1. What I get here then is, let's do it up here. I get 3 plus 2 lots of 1, so that's 5, minus 2 plus 4 lots of 1, so that's 2, and then 1 plus 3 lots of 1, giving us 4. So in that case then, what I get here is 5, 2, 4, and 5, 2, 4 here is the position vector of the point of intersection, of where's the point A, right? So 5, 2, 4 here is the position vector, of A here, okay? In other words, the point of intersection. So there we have it then. Hopefully nothing too challenging there for part B. Now, for part C then, let's just scroll up here and read part C. It says, briefly explain why this does not mean that the two helicopters will necessarily collide. So what we're saying here then is that the helicopters do pass through the same point, but this doesn't necessarily mean then that they pass at the exact same time. And that's all we need to mention here, right? So the helicopters pass through the same point, but not necessarily at the same time. Necessarily, I hope I'm spelling that correctly, not necessarily at the same time. Okay, and that's all we need there for part C. I think it was just 1 mark, right? So yeah, just 1 mark for part C. That's absolutely fine there. Now for part D then, what we're told here. So we're now given that the point B here has this position vector 9, 10, 10, and we want to show then that the point B lies on the line L1. Again, just one mark here, nothing too challenging. So we have 9, 10, 10. So this lies on L1. Well, let's just scroll up here. So for the vector equation then of L1 here, basically for some value of lambda here, this should give us this position vector, 9, 10, 10, right? And if I just look, for example, here, right? 3 plus 2 lambda must be equal to 9. So just make a note here. 3 plus 2 lambda is equal to 9. Just solve for lambda, right? So 2 lambda is equal to 6, and therefore lambda is equal to 3. So if we say then, when I can speak here, I'm losing the ability to speak. So let's just set lambda equal to 3. Okay. Then what do we get here? So we obtain that R is equal to, so we had 3 minus 2 and 1 plus lambda times 2 for 3, but lambda here is 3. So 3 lots of 2, 4, 3, like so. And we just evaluate this here then. 3 plus 6 is 9. Minus 2 plus 12 is 10. And then 1 plus 9 here also gives us 10. So therefore, we can say then that the point B, so therefore B lies on L1 there. Okay, hopefully, again, just one mark here, hopefully nice and straightforward. And then for the final part of this question here, part E, we're given that the acute angle between L1 and L2 is 33 degrees, and we want to determine the shortest distance between the point B and the line L2. Okay. So to finish with here then for part E, what do we need to do here? Well, all I'm going to do here is just use a bit of trigonometry, right? So for the shortest distance here, so this is from B to L2. What can we do here? Well, I'm going to represent this here as the vector D. Oops, I didn't want it to do it as a circle. Why won't it let me get rid of that? I don't know. Let's try again. There we go. So the vector D here, so that's better, is equal to then the magnitude of the vector BA times by sine of alpha, where alpha here is going to be the acute angle between L1 and L2. Okay. So for the vector BA here, this would simply be the vector OA minus the vector OB, right? Just dealing with position vectors here. Again, there shouldn't be anything too challenging, I don't think. So the vector OA is 5, 2, 4. So 5, 2, 4 minus the vector OB, which is 9, 10, 10. Okay. If we evaluate this here, what do we get then? So we get minus 4, minus 8, then 4 minus 10, giving us minus 6 here. So the vector BA is minus 4, minus 8, minus 6. So what I need here then is the magnitude of this vector, and I times that by sine of alpha. Alpha here will be 33 degrees. Just make a note of that as well there. So in that case then, the vector D here is equal to the square root then of, like we said here, we take the magnitude of this vector here. So that's minus 4 squared plus minus 8 squared plus minus 6 squared. Okay. And then we times this here by sine of alpha, where alpha is 33 degrees. Okay. At this point here, just use a calculator. I haven't done this myself, so let me just quickly do this on my calculator here. So what do I get here then? So the square root of minus 4 squared plus minus 8 squared plus minus 6 squared, that is the square root of 116. So square root of 116 times sine 33 degrees. And if we just evaluate this here then on our calculator, the square root of 116 times sine of 33 here, obviously just make sure then that your calculator is in degrees mode as opposed to radians. What we get here then, does it ask for it to 3 significant figures? It doesn't ask for it to any degree of accuracy here, so I'll just give it to 3 significant figures. What I get here then is 5.87. So 5.87 units there, okay? And there we are. So this here is the shortest distance from or between the point B and the line L2 there, okay? And there we have it then. So, not the easiest vectors question, but certainly not the most challenging. But there we have it. So that gives the solution there to question 7. And then finally, to finish with here, we have the very last question, question 8. So let's just go step by step here for question 8. It's quite a long question. So let's just quickly begin here by reading the question. So I don't want to go into too much detail here. As you can see, there is a little bit of context for the question, but basically what we've got here then is a scientist who is examining the rates of change of 2 different types of chemicals, X and Y, in a tank of water. I've got the rates of change then for each chemical here, and they're modeled by the following differential equations. Okay, X is the number of liters of chemical X, and Y is the number of liters of chemical Y at time t hours. So pretty standard stuff here just to get started then. For part A, all I want to show here is the following. So this question here is on coupled first order differential equations. And the first part of the question here is pretty standard, right? You just want to obtain the second order differential equation. So to get us started here, let's just call this differential equation here equation 1, and then this differential equation here equation 2. Okay? So to get me started here then with part A, what I'm going to do here then is rearrange equation 1, making Y the subject. Okay? And if we do that here then, what we get is Y is equal to 1 over 3 dx by dt. So 1 over 3 dx by dt plus 4 over 3 x there. Okay? And let's just call this equation here equation 3. Okay? Now for the next step then, what I'm now going to do here is differentiate with respect to t. Okay? So if we do that here then, what we get is dy by dt. So dy by dt here is equal to the following. So I get 1 over 3 times the second derivative of x here. That's d squared x over dt squared plus 4 over 3 dx by dt. Okay. What I'm now going to do here is substitute this into equation 2. So now sub into equation 2. Okay. And just recall then, this is equation 2 here. So if we do that here, I get 1 over 3 times the second derivative, that's d squared x over dt squared, plus 4 over 3 dx by dt. So this here, if I just scroll up then to equation 2, that's dy by dt. I've also got 2x plus y, and y here is equation 3, right? 1 over 3 dx by dt plus 4 over 3x there. So this here then is equal to 2x plus y, where y is 1 over 3 dx by dt. So 1 over 3 dx by dt plus 4 over 3x there. Okay, so let's just simplify here then. I can't do anything with this just yet. So that's just 1 over 3 times the second derivative here, like so. I've got 4 over 3 dx by dt minus 1 over 3 dx by dt, so that's just 3 over 3 dx by dt. That's just simply dx by dt there. Oops, why has it done it as a square? That was not intended. Let's just quickly get rid of that. So we'll try again. So dx by dt here. There we go. That's better. And then finally, 2x plus 4 over 3x, that is 10 over 3x. So subtract that off both sides, right? We want the right-hand side here equal to 0. Get minus 10 over 3x there. And this here then is equal to 0. So to finish with here, right, all we need to do now is just times through by 3. And therefore, what we get here then is d squared x over dt squared plus 3 dx by dt minus 10 is equal to 0, exactly as we require here. So as required there, and there we have it then. So that gives us the solution here to part A. Now for part B then, what do we want to do here? Well, we want to show then that the general solution for the number of liters of chemical X at time t hours is the following here. Now to do that then, what I need here is our auxiliary equation. So for the auxiliary equation here, that is just formed from this second order differential equation here. So we get m squared. So m squared plus 3m minus 10 is equal to 0, right? Now what I'd hope here is that this factorizes, and the good news here is that this does indeed factorize. So what I get here then is m plus 5 times m minus 2, okay? And this here then is equal to 0. So this gives us two solutions. We obtain m is equal to minus 5, and then for this solution here, m is equal to 2. So, writing this then as the complementary function here, or in other words, as the general solution then x here. So x then is equal to ae to the minus 5t plus be to the 2t there, okay? And there we have it then. So that gives us the solution to part B. So what do we want to do here then for part C? So let's just scroll up here. So for part C then, we now want to find the general solution for the number of liters of chemical Y at time t hours. So pretty similar to part B, but there is a little bit more work involved here for part C, okay? Let's just do this underneath here. Now for part C then, what we now need to do here is differentiate x here, this general solution from part B, and substitute that into equation 3 here, okay? So if we differentiate x here, what do we get then? So dx by dt here, hopefully nice and straightforward then. So I'm just differentiating x here with respect to t. So that's going to be minus 5a e to the minus 5t. So minus 5a e to the minus 5t, like so. And then for the second term here, that's going to be 2b e to the 2t. Okay, so plus 2b e to the 2t there. Okay, now like we said then, let's just substitute this into equation 3 here, where x is equal to this, and dx by dt is this here. Okay, so therefore then, substituting this into equation 3, y is equal to, so we get 1 over 3. So 1 over 3 times by minus 5a, so minus 5a e to the minus 5t, like so, plus 2b e to the 2t, e to the 2t there, like so, plus 4 over 3 then, times by x here, where x then is ae to the minus 5t plus be to the 2t. Okay, so altogether then, we get 4 over 3, ae to the minus 5t plus be to the 2t. Okay, so all I need to do here then is just simplify this. So let's just begin by expanding And then we'll just collect like terms where we can. So y is equal to get minus 5 over 3 ae to the minus 5t plus 2 over 3 be to the 2t plus 4 over 3 ae to the minus 5t, and then finally here, plus 4 over 3 be to the 2t. Okay, that looks good. So let's just collect like terms here and simplify where we can. So minus 5 over 3 ae to the minus 5t plus 4 over 3 ae to the minus 5t. That just simplifies here to give us minus 1 over 3. So minus 1 over 3 ae to the minus 5t there. Like so. I've then got 2 over 3 b to the 2t plus 4 over 3 b to the 2t. So that is 6 over 3 b to the 2t, which is just simply 2b. So 2b e to the 2t there. Okay. And this here then, this is for y. And this here is our general solution for, what was it asking for here then? The general solution for the number of liters of chemical Y at time t hours there. Okay. So there we have it then. This here is the solution to part C. So for part D, then what do we want to do here? So let's just quickly read the question, or this part of the question anyway. So we're given that there are initially 4 liters of chemical X and 1 liter of chemical Y in the tank. So for part D then, what we want to do here is express X and Y as functions of T. So let's just scroll down here then and have a go at part D. So what we're saying here is when T equals 0, so when T equals 0 here, X is equal to 4 and Y is equal to 1. So what I can do here is actually form simultaneous equations, right? By using our general solutions here. So X here is equal to AE to the minus 5t plus BE to the 2t. So when T equals 0 here, I get A times 1, which is just A, plus B times 1, which is just B. So A plus B is equal to 4. Okay. We get A plus B is equal to 4. And doing the same here then with Y. So Y is equal to 1. So I get minus 1 over 3 times AE to, well, E here is to the power of 0, right? Because T equals 0 here, that's our initial condition. So minus 1 over 3A times 1. Just get minus 1 over 3A. So minus 1 over 3A here. Doing the same then with B here. So 2B times 1 is just plus 2B. And this here is equal to 1. Okay? And all I need to do here then is just solve these simultaneous equations. It's completely up to you how you do this, right? You can just use your calculator. You can just times this top equation by 2 and then just go on to solve the simultaneous equations. But either way, this should be pretty straightforward. And what you should get here then is 7 over 3a. 7 over 3a is equal to 7. Therefore, in that case, then a is equal to 3. And then for b here, b is 1. So a is equal to 3 and b is equal to 1 here. So in that case, then x here. So all we need to do here is just rewrite our general solutions then with these values of a and b. So starting off with x then, which is ae to the minus 5t. So that just gives me here 3e. So 3e to the minus 5t plus e to the 2t. Okay. So that's x there. Don't forget y here as well. So y is equal to, so again, just replace a with 3 and b with 1. So what I get here then for y is get minus 1 over 3 times a here. So that is minus 3 over 3, which is just minus 1, right? So minus e. So minus e to the minus 5t there. And then for 2b here, well, b is 1, so that's just 2e to the 2t there. So plus 2e to the 2t there. Okay. And there we have it then. So nice and straightforward. That gives us the solution to part D. And then finally here to finish with, we have part E. So just dead quick here then for part E, it just says by considering what happens over a longer period of time, briefly comment on the suitability of the scientist model. So to finish with here then for part E, all we need to consider here is what happens as t tends to infinity. So as t tends to infinity here, what would happen? Well, I've got e to the minus 5t here. So e to the minus 5t here, this will just tend to 0. That just tends to 0. And then for this exponential term here, e to the 2t, so e to the 2t will tend to infinity. So in that case then, x here, so x of t, so x of t, as t tends to infinity here, will also tend to infinity. And the same is true here for y of t. So y of t will also tend to infinity. Okay, so to finish with here then, all we say here is the model is unlikely to be suitable over a longer time period. Okay, basically what it's saying here then is x and y just grow without bound, right? So they just keep growing and growing, which in a real life situation is not likely to be practical. So the model is unlikely to be suitable over a longer time period. Okay, and there we have it then. So that's all we need there for part E, right? Just, considering what happens as t tends to infinity. And there we have it then. So that gives the solution here to the very last part of question 8 here, part E. And that actually gives us the solution then to the very last question, question 8 of this predicted paper or this mock paper here, set A, paper 1. If you made it all the way to the very end, thank you so much for watching. As always, I do appreciate each and every single one of you who does watch our videos. And as always, thank you for watching and good luck with your upcoming Core Pure exams.